So the talk will be about mechanized and constructive reverse analysis of soundness and completeness of Bi-intuitionistic logic. And the talk will be given by Dominik.
Yes. Only give me 1 second, sorry.
Yeah, sure.
In the meantime, I can say that this is joint work with Goré and Shillito, who is, oh, that's interesting. Does that work? So here you see work in progress, but I want to show you some work that is done. Sorry. I'm getting there. Maybe I have to. Oh, yeah. Okay, so I was starting to say that this is joint work with Goré and Shillito, who is not here. He couldn't make it because he prefers to enjoy the Australian summer. So I'm giving the talk on his behalf. And once I've finished showing you the slides, I can actually start. So almost there. Displays, arrangement, mirror. Aha. That should make it better. Yeah. Okay. And this. Okay, that looks all right. So now one more thing. Maybe this works. Yeah. Okay, I can start. Sorry for that. I'll try and make up for that time loss. So I can leave out reading the title again because Sandrine has done that already. So what I will start with instead is explain to you very quickly what bi-intuitionistic logic is if you haven't seen that before. Basically, it's an extension of intuitionistic logic, which you might have seen before by adding a dual to implication, which is usually called exclusion. And to explain why it's a dual, I remind you of the usual rule how implication is interpreted in intuitionistic logic over some Kripke structure. Then at some world W, you say that an implication is forced if for every successor worlds, if these successor worlds force the premise, they're supposed to also force the conclusion. And now the dual to that, which is exclusion, opala, interesting. Sorry for that. So for me, it seems to even skip more slides than one. So the dual to that would mean that there is, or for all previous worlds, all predecessors, we don't have the case that an implication is forced. Or if you look into the literature, you see maybe an equivalent formulation which says actually there is some predecessor for which the premise is forced but not the conclusion. So this is kind of the semantic side. You just flip some quantifiers and then say this is a new connective. If you then look at the syntactic side and want to see what a proof system for that could be, you identify certain axioms. For instance, you see that you have the axiom that for every formula, either the formula holds or true excludes that formula, which is kind of a dual to negation. So this is some form of a classical disjunction, which however holds because if you look at it, it unfolds into at some world either a formula, oh, that should be psi, is forced, or you have a predecessor where it is not forced. So that's kind of the overview of intuitionistic or bi-intuitionistic logic. You can do that on propositional logic, you can extend it to first order logic and so on. Now, actually, bi-intuitionistic logic by its history is a very nice case for computer mechanization, because if you look in like the origins in the literature, you see that there is some discussion, or the semantics is introduced by Grzegorczyk and then proven complete by Klempke in the Henkin-style completeness proof. And then the person who looked into bi-intuitionistic logic most detailed is Rause, who gave a lot of investigations about soundness, completeness, many meta-theoretic properties. However, some of her proofs were found to be incorrect. The proofs were on paper, and then my co-author Ian and his PhD supervisor Rajiv Goré found that there are errors in that proof. They fixed it for the propositional case, and Ian has mechanized the propositional case already in his PhD thesis. So now what we have is the state that we now, soundness and completeness are correct, at least in the propositional case. They have been verified in the Coq proof assistant. So I could now explain that, well, this formalization worked, we were using standard techniques and so on. But actually what I want to focus the talk on is something you could do on top of this if you work in a formal setting anyway, in particular in the setting based on a constructive meta theory, like Coq's underlying type theory. Namely, you can analyze in the style of constructive reverse mathematics what the logical strength of the properties you have established really is. Meaning that if you work in a weak constructive system, you see that many different logical principles can be distinguished, and then you can analyze which of these principles connect to the theorems you have proven. So the mother of all these principles is the law of excluded middle, stating every proposition is true or false. And if you accept classical logic, the story ends there. But in constructive logic, under the hood, there's much more. You can look at, for instance, there's weak excluded middle, which is a restriction, a strictly weaker restriction to only negative propositions. Then there is a principle called double negation shift, which allows you to pull out double negations below universal quantifiers. And there's Markov's principle, which is basically double negation elimination for sigma 1 properties, or for solvability of Boolean sequences. All of them are disconnected. It's a sequence of more and more weaker principles, and all of them can be analyzed in the style that you can look at certain classically valid theorems and then get an idea which of these theorems may be equivalent to which of these principles. And that's the idea of constructive reverse mathematics, which doesn't only tell you something about the logical strength of the theorems you look at, but also about the computational content. Because, for instance, some of these principles, like double negation shift or Markov's principles, do have a very natural computational interpretation. So if you show that some theorem is equivalent to one of those, you also have a natural computational interpretation of that theorem. Okay, so to give you a warm-up example, we first look at the case of soundness very quickly. If you look at soundness and remember that there is this axiom that kind of looks a bit classical, you can get an idea that soundness might not work right out. So soundness is the property that every derivation in the syntactic system is valid semantically. And here indeed what you need is, for instance, that you just look at models that satisfy this property. Not every model in a constructive meta theory necessarily satisfies this property because it gives you some disjunction for free. So instead, what you can prove is, well, soundness holds for every model satisfying these critical axioms. In particular, if you have the excluded middle around, every model will satisfy these axioms, and then you're good, then you can show soundness. And now the question of constructive reverse mathematics is that all to it, or can we do better? And the answer is, well, we can't do better. We can reversely find that soundness implies excluded middle. And the proof is pretty simple. What you basically do is you assume some proposition, you look at a trivial model. Since that model is assumed to be sound for the rules, you get a disjunction for free from which you can then analyze whether P or not P was the case. So that's kind of the blueprint of a proof in constructive reverse mathematics applied to bi-intuitionistic logic. You see soundness is completely classical. Okay, now, since you have digested that idea, we go into the much more subtle case of completeness. Completeness meaning the opposite of soundness. From validity, you get derivability. And in fact, not even for bi-intuitionistic logic, but if you look at the literature, which is pretty rich in the case of first-order logic, you see that funny things are going on. So there's a lot of papers published claiming, rather different equivalences. You don't have to know what these principles here really are. The only point is they are actually incomparable. Yet still, there are papers in the literature claiming, well, completeness has logical strength, exactly this. And even more funny so, in the literature, there's also a paper claiming there's a fully constructive proof, not needing any principle. So we have been puzzled by that for quite a while and confused and trying to understand what's going on. And basically what is going on is that there's many different things at play, and it really depends what formulation of completeness you choose and which kind of constellation of different dimensions you use that contribute to the status of completeness. So just quickly, things that can play a role is which syntax you're actually interpreting, what complexity of contexts you admit, what the cardinality of the signatures is, what the representation of the semantics is. All of them can be chosen independently. They don't really contribute independently to the status of completeness, so there's even some interplay going on. So the situation, the landscape is really rich. And what this led to was that first started by Hugo Herbelin and Danko Illich. They looked at first order completeness theorems in a constructive setting, and then my group at that time jumped on it and tried to develop a few more ideas. We found out a few more ideas, and one of them I will explain to you now at the example of bi-intuitionistic logic, which is for a very specific constellation, but explains exactly what is going on if you have disjunction in the syntax, which is kind of the evil principle which turns into decisions on meta level. Okay, so to look at disjunction, let me remind you how a completeness proof would look like for propositional intuitionistic logic or bi-intuitionistic logic. What you normally look at is a universal Kripke model in which membership in the worlds coincides with forcing at that stage. And usually this universal model is constructed over the prime theories, where prime theories are classically behaving theories in the sense that if they contain disjunctions, they tell you which of the disjuncts they contain. And this is needed to interpret disjunction. Then one technical device is the so-called Lindenbaum extension, that you can take any consistent context and turn it into a world of that model by extending it until it gets prime. You saturate it so that enough disjuncts are contained. Then from this, you show that you can construct this universal model in which the truth lemma holds, which is the coincidence of membership in worlds and forcing at that world. From that, you then derive model existence, so every consistent context has a model, namely the universal model. From there, you get to a classically invisible step, which plays a very important role constructively, which is quasi-completeness. So from validity, you can derive not derivability. Classically, you just eliminate a double negation. From there, constructively, you will have to do something else, again, depending on other aspects of the constellation you are in. So that's the classical outline. Let's see what changes if we turn to constructive logic. Well, everything turns pretty bad. In particular, already in the very first part, we have no chance of constructing quasi-prime theories because this would require us to make a lot of decisions. The best we can actually do is a property we call quasi-primeness, which is primeness up to a double negation. So you hide the actual decision you made. But if you do that, you can only form the universal model over those because you need to be able to extend theories into worlds of the universal model. And even earlier, if you then try and prove the truth lemma, you notice that this proof is always by contradiction. So showing membership in theories will always be argued negatively. And again, that is a thing you can't do in constructive logic. So the first attempt fails completely, but you can look at it a bit more carefully, which gives you already a bit more hope. Namely, you can observe that the Lindenbaum extension is actually a negatively described iteration process. It says it characterizes membership in an extension by non-derivability, so by a negative property, which in turn makes the membership in such an extension double negation stable, meaning you can argue membership in a theory by contradiction. So you have a bit more hope. You can still use the same universal model, still start on proving the truth lemma. You can argue classically for membership in the theories, but then you're blocked at the exact case of disjunction. And why are you blocked at that exact case of disjunction? Well, if you look at this case, disjunction or the case of the truth lemma here means that a disjunction is member in a theory if it is forced at that world. Now, forcing at that world is defined by disjunction in the meta-logic. By inductive hypothesis, we thus have to make a decision of membership, which is exactly the primeness property, which we can't get. So there's no way around to establishing this primeness property, and also constructively, there's no hope of extending it for certain connection to Gödel incompleteness. So the only thing we have to know or do at that stage, which is left, is, well, we assume some classical axioms and hope that they are exactly characterizing what is going on. And one thing that we found is that the weak excluded middle plays a role, in the sense that if you assume the weak excluded middle, then every such stable quasi-prime theory that we get for free constructively can be considered to be prime. And the idea is, if you remember, weak excluded middle was excluded middle for negative propositions. Since membership in stable theories is negative, you can just do case distinctions. So the proof is pretty straightforward. You just start with some disjunction, use the weak excluded middle on membership, and then eliminate the double negation you get. So what we know from there is that if we throw in the weak excluded middle, then we can re-establish the original proof outline, and even more so, we get up to model existence and quasi-completeness, these intermediate statements of completeness. Now, playing the game of reverse mathematics, we are interested in finding out if we can do better. And we found that you can't do better, because if you assume model existence, from this you can derive backwardsly the weak excluded middle, meaning model existence has exactly the logical strength of the weak excluded middle, and the proof is by just, on assumption of some proposition P, using a context that we manufacture in a way that it gives us some information on top. It contains a disjunction, then it contains membership depending on the proposition P. Then the whole trick is that consistency, being a negative property, can be established constructively, but then positively model existence would give us a model which has to make a decision for this disjunction. We can analyze it and then derive a case distinction for P. That's the whole idea. There's nothing very deep going on. So what we can now think is, well, we know that equivalence for weak excluded middle. Can we go one step further? What about quasi-completeness, this weaker principle following from model existence? And there, if we try the same, we find that actually we cannot derive the whole excluded middle, but a principle that looks a bit strange maybe at first sight. It says if you have a predicate, then it is not the case that the weak excluded middle holds for that predicate. So in particular, this follows from the weak excluded middle, and this implication here can be done basically by using similar tricks. And now we could wonder whether we were just not doing well enough, and maybe there should be a proof of the weak excluded middle from quasi-completeness. But since we also can prove quasi-completeness from double negation shift, this other principle I showed in the beginning, which allows pulling out double negations, there is no hope to actually derive quasi-complete or weak excluded middle, because then by composition from double negation shift, we would have gone to weak excluded middle, and weak excluded middle behaves much more classical than double negation shift. So there's no hope doing that. Instead, so let's first look at this principle a bit more closely. We call it weak law of excluded middle shift because it can be seen as shifting a double negation through a statement of weak excluded middle, or you can also formulate it more symmetrically if you want, then it looks a bit like a De Morgan principle. And what it can give us applied to this business of completeness is that it shows us almost what weak excluded middle did. So every stable quasi-prime theory, the thing we get out of the Lindenbaum extension, now is not prime. So we can't get rid of this double negation here. Basically, it's the same proof as before, using the weak excluded middle, but just a double negation remains at the end. But the nice thing is the way the Lindenbaum extension is needed in the completeness proof, in the proof of the truth lemma, just so happens to be that it's always within a negative context. So always you just need this property when you are able to eliminate this shielding double negation. And this means that actually from this principle, you can derive quasi-completeness. And the proof outline is basically as before. So you are now happy with the Lindenbaum extension being slightly weaker than what you actually need for the universal model, because the universal model has to be about the prime theories. Then the truth lemma can be established, as I said, because in all critical cases, you can get rid of the double negation shielding the Lindenbaum extension. And from there, you then get something slightly weaker than model existence, which, however, is still strong enough to give you quasi-completeness. And so, in summary, what we have is weak excluded middle equivalent to to model existence, and weak excluded middle shift is equivalent to quasi-completeness. And from there, you could now go on and analyze, well, how do I get rid of that double negation? For instance, this now really depends on the logical complexity of the context, but in the case, if the contexts are enumerable, for instance, the Markov principle will suffice. So there's kind of a story to tell there that you can find weaker logical assumptions to get stronger completeness results. Okay, I hope all of that was somewhat clear to you. If not, you can ask a lot of questions. Let me summarize with that slide here, which first tells you that doing these things in a formal setting is extremely worthwhile. So first, of course, doing these proofs in Coq that have been erroneous before gives you a certain guarantee that this time you got things right. Then on top, you can play this whole game of doing reverse analysis, which is extremely intricate because there's a lot of double negations everywhere. And you want to do that in a proof assistant that actually helps you manage all the ideas. And also because you sometimes have to change subtle things in a definition or a theorem, the proof assistant tells you exactly where to do these changes. These two arguments work for every proof assistant. Now, for the particular case of Coq, the nice thing is that it has an extremely weak logic, which doesn't even prove principles like the unique choice axiom, which allows you to do this whole classical analysis. You can assume very, very weak logical principles, show them equivalent to certain theorems, while still assuming the computational properties of that system. Okay, so that's kind of the reason why Coq was the proof assistant of choice for that project. Now to give you an idea of the future plan. So one thing we are still puzzled about is we now know, for instance, if we are looking at completeness for enumerable context, semi-decidable context, which is kind of the basic case if you look at axiom systems like piano arithmetic or something, they're usually computational tractable in the sense that they are at least semi-decidable. And we know that completeness in that case would follow from weak excluded middle shift plus Markov's principle. What we don't know at the moment is whether something weaker than weak excluded middle shift would suffice. So there's some gap in between where we don't know which logical restriction we can put on the properties here, which would then turn out exactly equivalent to the completeness result. Then I mentioned something called the Fan theorem in the very beginning as one canonical thing shown equivalent to completeness theorems. And we conjecture that the principle we discovered here is kind of one logical contribution to the Fan theorem, which normally becomes only visible in a certain other constellation of the statement. So we think that there's a story to tell there, that you can decompose the Fan theorem into something talking about fans and something logical just talking about decidability of fans. Then we are not very clear because we chose this particular semantics for bi-intuitionistic logic, interpreting exclusion negatively with a negated for all quantifier instead of positively with an existential quantifier. And we don't yet have an answer how this would behave constructively. And even more so, the whole game we played was for propositional bi-intuitionistic logic. There isn't even a formalized proof of first order bi-intuitionistic logic completeness, so that's the next thing we're going to work on. And then you might have noticed that everything I explained about this constructive analysis was completely independent of bi-intuitionistic logic. So basically, we think that these observations are kind of universal, that in any logic that you have, for instance, that interprets some syntactic disjunction as meta-theoretic disjunction, you will have a connection of model existence with weak excluded middle, with quasi-primeness, with weak excluded middle shift. So there's a lot of stuff still going on, but I'm going to end here and leave some room for questions. Thanks.
Thank you. Are there any questions?
Hi, Cezary Kalishik. It's a very nice talk, thank you. I was wondering about this fine-grained analysis. It's clear to me that constructive type theory is the right foundation for making it clear what is needed, what's not. But when it comes to the actual use of COC, how are you analyzing the proofs? How easy it is to extract the information from COC? What was there, what was not? So, I mean, you kind of gave some hints, but like, are you looking at the proofs on the level of the vernacular of the proof scripts, or are you analyzing the proof terms, some things for dependencies? Could you imagine things from proof theory for restructuring of the proofs somehow semi-automatically that would allow it to be done easier?
Mm-hmm. Thanks. Yeah, so at the moment we've just been looking at it on logical level. So we prove equivalences in COC, and we don't look at proof terms. We don't look at the realizers attached to it. In principle, what you can do is you can place the whole discussion into the non-computational layer, into the computational layer of COC, and then extract a completeness proof in the form of an algorithm that kind of reifies a meta-level proof term into an object-level proof term. But if you do that, you lose one of the nice points about COC, that you have this distinction of the logical and the computational layer, which allows you to assume classical logic at the same time as interpreting the computational layer as computational. So you can do all of the analyses up to the point where you look at, say, completeness of enumerable contexts, because if you look at this on the computational layer and throw in something that tells you the computational layer behaves classically, then suddenly every predicate will be enumerable. So you cannot make these distinctions anymore. So you have to be a bit careful about that.
Thank you. If there's no one, I can ask one more, but...
I think we have time for both questions.
Hi, Ruben Rowe, Royal Holloway, University of London. I was very intrigued by your final comment, which was that your analysis sort of holds irrespective of the nature of bi-intuitionistic logic or the semantics. I'm just wondering whether you see a more or less straightforward way of formulating that intuition, in a general abstract way and then proving that, or you haven't sort of no idea.
Yeah. So if there would have been a very straightforward way to do it, then we would have done it. I think one approximation we can do is
there's always a time constraint, isn't there?
Yeah, that plus it's hard to like formulate abstractly what it means for logic to have a disjunction that is interpreted in. You even want to generalize about the semantics, so you don't want to fix to the case of Kripke semantics or Tarski semantics. All of this also works for Tarski semantics. Always, if you turn some syntax into like the meta level by interpreting disjunction with disjunction and so on, then these effects will appear. I think what can be done is we have this formal framework for first order logic, which is parametric in types of quantifiers and logical connectives you put in. And this gives you kind of some abstract grip of, for instance, you can cast bi-intuitionistic logic in that setup, and every logic that can be captured by just extensions of first-order logic with additional quantifiers, additional connectives, I think even modalities could be cast into that. Then you can, for this class of object logics, you can do it directly in that setting. If you want to do that now for type theory, well, then you would have to generalize much more.
All right, thank you.
Maybe a last question? Yeah.
In the middle of your talk, you said the logic of Koch is somehow weak. So I was a bit surprised by this. I understand what you mean that, say, in whole, you would not be able to do it because of the classical axiom and several other things that make this kind of analysis impossible. Mm-hmm. But if I think about Koch, there are quite a number of things assumed there that go beyond the simplest constructive type theories. And so that's what I was starting to wonder about. Are there features of the logic of Koch that actually make some kinds of analysis impossible, where doing this in, I don't know, LF or just plain COC would make it fine?
Mm-hmm. Yeah, very, very nice. So first of all, weakness, I think, in that context is the correct word, because weak systems are strong for reverse analysis. So the weaker the system, the finer the lens. And now, indeed, Koch has some features that blur the analysis. So, for instance, one version of the fan theorem is provable in Koch, the very propositional version of it, because Koch has full comprehension. So you cannot analyze write out the contribution of the fan theorem, but there's a trick to circumvent that. If you instead put the semantics, instead of propositional layer, you put it on Boolean layer, but then you have other defects. So there's a certain way where Koch is too strong. Then also you have this feature of impredicativity, which I'm pretty sure is not needed in that analysis. But also there you could imagine an even weaker system that tells you more general, more strong results indeed. Yeah.
Thank you.
But I think, on the market, I think this, in established proof assistance, this one is the weakest one in the sense of reverse mathematics.
Thanks.
Okay. So thank you again, Dominik.
Sure.